Hello, everybody. It's a pleasure to see so many of you at a purely technical talk at Track 1 at DefCamp. First thing first, how many people here know what DLLs are? Wow, lots of hands up there. I love that. Second question, how many people here have found DLL hijacking vulnerabilities in the past? Okay, that's probably a quarter. And how many of you guys pen test Windows applications regularly as part of your day-to-day job? Okay, very few hands up there. That's fantastic. Great, so let's jump straight in. A bit about myself. I'm Matei Anthony Josephs, a senior penetration tester at KPMG. I have some experience in vulnerability management and people management, same but different. However, lately I focus mostly on developing as a penetration tester and building a company alongside my amazing wife. In terms of learning and education, I've got a degree in criminology with psychology and a master's in cybercrime and intelligence from the University of Portsmouth. In terms of certs, I have the OSCP, EWPT, CRTO, and a bunch of other ones which you can find on my LinkedIn. Now, last important point here, I have discovered 4 CVs this year, or at least 4 of them are confirmed, 2 of which are DLL hijacks. Any reverse engineers in the room? Okay, a few. So I bet you guys use PE Studio. One of the CVs is a DLL hijack in PE Studio, and I'll talk about that. So, what am I trying to achieve from this talk? It should be a deep dive into DLL hijacking, or at least as deep as we can go within 30 minutes. If everything goes according to plan, this should take about 20-25 minutes, giving you enough time for questions. Other than that, I hope it'll be practical and exciting for you. I tried to make a live hacking session, but there's so many things which can go wrong with live hacking. So I said, okay, let's do some videos. Hopefully it will be equally exciting. As for you, what can you get out of it? If you're more of a beginner, maybe you can find your first DLL hijack. If you're more advanced, maybe you'll be able to improve your DLL hijacking workflow, and why not get your first CVE? So why have I chosen this topic? Well, there's a few reasons. Firstly, I get the sense that penetration testers usually focus on web apps, infrastructure, maybe these days cloud and APIs. But Windows executables have been put to the side. Windows executables have not been given the attention that I believe they deserve. Now, also, DLL hijacks are used by red teams and threat actors everywhere for persistence and, in some cases, privilege escalation. Also, I bet that every one of you uses software that is vulnerable to DLL hijacks. For instance, Microsoft Teams, OneNote, OneDrive, and Microsoft actually states that they will not fix these issues. Fantastic. So now we can delve right into it. But before going into DLL hijacks, let's take a step back and attempt to understand what DLLs are. DLLs, or dynamic link libraries, are Microsoft's implementation of shared libraries. They're very similar to executables in the sense that they use the same PE, or portable executable file format. However, they're not directly executable. Instead, another executable or DLL should load them in order to run. So you may ask, why do developers use DLLs? Well, there's a plethora of reasons, but here are a few. Firstly, they're modular. This means that if you want to change a feature, you don't have to go through the whole code base. Simply find the DLL responsible with that feature, modify the code behind it, and there you go. Secondly, they're reusable. So if you want to reuse the same feature across multiple applications, you can simply just use the same DLL. And lastly, they're memory efficient, or at least some of them are. So they don't all load all functions at runtime. Some of them load them when you actually call those functions. Fantastic. So now that we know what a DLL is, we can try to create our own. So here is a very basic proof of concept in C. What it does, it displays a message box with POC as the title and DLL hijack as the caption. We will cross-compile it using the -shared flag, and there we have it, our poc.dll file on our Kali Linux machine. We will now transfer it to our Windows machine, where we will execute it using run DLL 32. And there we have it. Our first message box, our first DLL was executed. Great job. So now we can talk a bit about DLL hijacks. And for this, I've created this little proof of concept in Python. What it does, it gets a handle on kernel 32 and then attempts to load two libraries using the load library W Win32 API function. Now, can anybody tell me the differences between these two load library W calls? Anyone? Yep, go ahead. Exactly. So right there, the gentleman said relative path versus absolute path. So the first DLL was loaded using the name only, relative.dll. The second one is loaded using the full path. So C, users, full DLL. So let's see why this matters. For this, we started procmon, and we'll set a few filters there. Procmon is a tool from the sysinternals suite. And our filters are result contains not found, and the path ends with full.dll or relative.dll. We shall start the capture, execute our script. Apparently nothing happens, but we can check our capture now. Okay. I'm quite aware that it's quite small, but I'll walk you through it. So there was only one attempt to load full.dll, just there at the bottom. Whereas there were several attempts to load relative.dll, starting from the Anaconda-free environments Py39 folder, then system32, then system, then Windows, and so on and so forth. This here is called the search order. I'm not going to go into too many details about it, because it could deserve a whole talk of its own. But the search order is the strategy of applications for searching for specific DLLs when mentioning only the name. Okay, so let's do our first DLL hijack. Let's imagine that the intended DLL is somewhere towards the bottom of the search order. Let's imagine it's in the load DLL folder right here. That's the intended one. Our malicious one can go somewhere towards the top of the search order, and in this way, we will have hijacked that DLL. So for this, actually the video restarted. That's not an issue. So once we retake that capture again, we shall go to the Py39 environment folder, make sure that we place our malicious DLL there, and see what happens in a second. Cool. So we place our DLL here. We rename it as relative.dll. We will go to procmon, scroll to the bottom of the capture, and run our script again. And we've got our message box. Amazing. We were able to hijack our first DLL. And as you can see here, there aren't that many attempts to load relative.dll this time. There's only one from Bromium, but that is HP specific and doesn't matter for this talk. What's important is that we managed to hijack our first DLL. And I could say, well done, guys. You've hijacked your first DLL. And I think this is a perfect moment for a checkpoint. In order to find DLL hijacks, we need the following. A few procmon filters, that is, result contains not found. The path should end with .dll. And also, the path should be writable by the user. You may notice an asterisk by the first filter. And that is that truly, it's optional. You could overwrite an existing DLL, and that would still be a DLL hijack. I prefer not to do that because it may alert blue teams, or perhaps it could crash the application, but that's pretty much up to you guys. So, before I go on, we saw that we are able to do a DLL hijack, and it's not too difficult when we're talking about 1 or 2 applications with a couple of DLLs. But what do we do when we're trying to achieve DLL hijacking at scale? Talking about tens, if not hundreds of applications. Here's where automation comes in handy. And here are links to my GitHub first, Matt Joseph's, and to Security Cafe blog. This is KPMG Romania's blog. All of the code snippets, which I'm going to show from now on, can be found on my GitHub, so don't worry about remembering them right now. But once you visit my GitHub, don't forget to check out AutoPy Delicious, or DLL-icious. I was trying to be a bit witty with the name. That's still work in progress. But this is my tool for automating the DLL hijacking process. And here is the procmon function. It's fairly basic. What it does, it terminates any existing procmon sessions and starts a new one, making sure to log everything into log.pml. Afterwards, once procmon is manually closed, we will open the log file and save it as CSV for easier parsing. And while we're on the subject of parsing, here's the parse logs function. We open the log file, the CSV file. We set the appropriate filters. Those are result contains not found, path ends with .dll, and then we iterate through the application paths and the DLL paths. We check whether the DLL path is writable, and if so, we save it to a dictionary, which will then reparse for friendlier formatting and return us potential underscore DLL. Here we've got a couple of functions. The message box present one, we attempt to connect to a window with POC as a title. You may remember that the proof of concept DLL that we showed earlier displayed the message box with POC as the title. So if we're unable to find this sort of window, it means that a message box was not produced. Otherwise, it means the message box was produced and we can return 1. Now, second function. This uses a Pythonic principle, which I quite like. It is easier to ask for forgiveness than for permission. Make sure you don't use that in real life, though. What we do, we open the path. We attempt to write a file there. If we're able to do that, great, we return 1, meaning that the path is writable. Otherwise, we return 0, meaning that we are sorry. Cool. And here is the function that does all the magic and puts it all together, the hijack function. We iterate through our list of applications. We iterate through our list of DLLs associated with those applications and copy our proof of concept into each DLL path one at a time. We shall then run the application associated with that DLL, wait for 2 seconds, and check whether a message box is present. If a message box is present, great. We were able to achieve a DLL hijack. We're able to hijack that DLL, meaning that we can log that into hijacked.txt before killing the process and removing the DLL. So I'm aware this was pretty quick, so let's see it in action, and I'm sure you'll understand it better now. So we run our script, give procmon a few seconds to start. We are prompted to run various applications, and I will run PE Studio, which I know for a fact is vulnerable. Okay, I started PE Studio. I can now close it, and I can close procmon as well. We will give the logs a few seconds to be parsed before getting a prompt to select the application which we want to test for DLL hijacks, and that will be PE Studio. Okay, we select PE Studio, that is number 2. And we can already see our first DLL hijack in textshaping.dll, our second one in MSASN1, and our third, crypt-based did not produce a message box. Okay, so let's check our hijacked log file. And we have indeed 2 DLL hijacks. textshaping.dll and msasn1.dll. However, cryptbase did not produce a message box. It was not hijackable. So this may actually raise the question, why weren't all DLLs hijackable? And there's a couple of possible reasons. The application could implement some sort of signature checking. We may or may not be out of luck in this case. Let's say the signature checking algorithm is weak, and then we use a tool like SignThief to spoof the signature. This may or may not work. Now, the second option is that the application checks for functions exported by that specific DLL. And in this case, we're lucky. You can actually find more details on Security Cafe. I've got a full article on this. But long story short, we find the intended DLL, extract its exports into a definition file, and then we make sure to recompile our malicious DLL using that definition file as well. So this way, we would bypass this check altogether. Great. Quick story. In the past year, I've tried DLL hijacks in pretty much every bug bounty program which has Windows applications in scope. And there's a dreaded line that keeps haunting me from there. That is, DLL hijacks without proof of privilege escalation are out of scope. Well, there's a specific situation where the application runs a system and it loads a library from a path writable by a regular user. Great, that's a fantastic privilege escalation scenario. But this is pretty rare based on my experience, or at least in bug bounty. So I thought, why don't I try to coerce the user into giving me administrative privileges? And for this reason, I created this short C program. Again, you can find it on my GitHub as well. What it does, it checks for the integrity level. So if we have high integrity level, meaning that we're administrator probably, we will return a message box saying, imagine this is a reverse shell. If we're not administrator, we shall display a message box saying, please run the application as administrator before entering an infinite loop, which prevents the application from running. Now, of course, the first message box, the imagine this is a reverse shell, could be anything. It could be an actual reverse shell, a beacon, or any malicious payload of your liking. But let's see it in action. So, I will paste my malicious file in the PE Studio folder as MSASN1. I shall run PE Studio, and I'm prompted to run as admin. Okay, I'm a good user. I'll run as admin. Okay, now imagine this is a reverse shell. You're an admin now. And now PE Studio runs as well. So this means that I'm the captain now. I'm admin. They were able to give me administrative privileges. I was able to hijack DLL in order to coerce the user into giving me administrative privileges. Great. Second short story. Remember the CV I told you about in PE Studio? That was in version 9.52. PE Studio is now at version 9.56. And what I showed earlier was in version 9.55. So how come PE Studio is still vulnerable to DLL hijacks, although they have a CV about it and they know all about it? And the reason is that CVs, or actually, sorry, DLL hijacks are surprisingly difficult to fix. And this is why. There's a design flaw. Let's say we load important.dll. That's the one we have control over. But then important.dll has a few prerequisites. Those are 1, 2, 3, and 4.dll. Now, no matter how we load important.dll, its prerequisites will be loaded using only the name by default. So not by a full path, only by the name. Meaning that even if we used secure coding practices to load important.dll, all of its prerequisites may still be hijackable. Now, for this very reason, vendors have pretty strict triaging policies when it comes to DLL hijacks. And here is Microsoft's one. So Microsoft may fix application directory DLL hijacks, so situations which I've showed today. They may fix them based on impact, based on how busy their developers are, and so on. They will definitely fix DLL hijacks related to the current working directory. So let's say we run the application, and the application loads a DLL from the current working directory. That's not good. That will be fixed. And they will not fix DLL hijacks related to the path environment variable. Don't ask me why, but you can check Microsoft's developer forum for this. But now we know how to create our first DLL. We know how to find DLL hijack vulnerabilities manually. We know how to create clever payloads to trick the users into giving us administrative privileges. What can we now do with all of this knowledge? Well, firstly, we can get CVs. I've done that. I have a couple using DLL hijacks. And if you do, let me know. Say thank you on LinkedIn. Second option, we can get bug bounties. Well, if you're luckier than I am, but you could get some extra cash. And if this presentation helped you get some bounties, great, let me know, buy me a coffee. Now there's a third option. You tried getting a CV. They said, not a valid submission. You tried getting a bug bounty, and they said, this is out of scope. Well, in this case, I hope that that piece of software is as popular as possible, because it will definitely be added to my Red Team toolkit. Thank you.
Thank you so much, Matei.
Thank you.
That was really insightful and a great delivery as well. So now we have time for questions. Let's start the party. Okay, over here.
It was a really nice presentation.
Thank you.
I was wondering how we can identify vulnerable DLLs that we do not have, that we are not authenticated on the Windows system.
Okay, that's an interesting question. Not entirely sure. I'll have to look into it. To be fair, just thinking about it right now, I'm not entirely sure if you could do this sort of thing unauthenticated. So sort of a prerequisite to exploit and find DLL hijacks would be to be logged into the system. But still, you could create, I don't know, your own sandboxes, your own VMs, and test DLL hijacks on there. And they will probably be applicable to the same versions of the application in a live system.
So the Windows has the same DLLs for each version, has its specific DLLs?
Yes, indeed. So it's not necessarily Windows specific. It could be application specific.
Ah, okay. Okay, that's all. Thank you.
Oh, fantastic. Thank you.
Okay, let's go to the next one. At the back there, please keep your hand up.
Yes, please.
Hello.
Could you speak up just a bit?
Okay. Can you hear me?
Yep, thank you.
Okay. Is there a reason why Windows doesn't implement a specific mechanism for blocking DLL hijacking? On other platforms, there are such mechanisms.
Yep, that's actually a really good question. So there are plenty of other platforms. You can find similar vulnerabilities in Mac OS and Linux. Not really the same, but similar. Well, I'm not entirely sure. I would ask Microsoft. To be fair, I find it a big issue that the design flow of the DLLs is the way it is. So I really don't understand why dependencies would be loaded using a relative path or the name only instead of a full path. And that would definitely be a place to look at first, in my opinion.
Okay, next
Yes,
question.
please.
Please keep your hand up.
Thank you for the presentation.
Thank you.
Very, very interesting. Have you tried this exploit on React OS as well?
No, I haven't looked into React OS. But let's do that together. Why not? Let's get in touch. Connect on LinkedIn, and we can see. Maybe we can find something.
Okay.
Great.
Cool. Let's take one more question there and one there. Those will be our last two questions.
Hi, thank you for the presentation. I'm wondering if you have an efficient way, a rule to detect such DLL hijacking, because legitimate software loads unsigned DLLs, and you need just to be aware of the order or.
Well, that's a very good question, actually. So here, I've looked at it only from an offensive perspective. Defenders, blue teamers can definitely check logs for this. So loading unsigned DLLs, as you said, would definitely show up in logs. But in my opinion, offense is still the best defense. So if we are proactive with our offense and we try to attack systems and know where they're vulnerable before they're actually exploited, we actually have an advantage over the actual attackers. But yeah, that's a good topic for a next presentation. DLL hijacks from a defender perspective.
That's one for next year. But until then, one more question over there. Please keep your hand up.
Hi, thank you for the presentation.
Thank you.
Could this be added as part of a toolkit with like privilege escalation and like vulnerable Windows versions? So you could like target if the, let's say, Windows version is vulnerable, then it wouldn't prompt you to like add to administration prompt.
Look, so WinPs and a few other PowerShell tools as well highlight these sort of issues. They can detect DLL hijacks automatically. But the reason for creating all of this manually was to actually move away from this sort of one-click exploit approach. So, I mean, it's so easy to find DLL hijack as the output of the tool, run MSF Venom and just hope for the best. Whereas here, I tried my best to actually show the whole process end to end. So in reality, yes, definitely you could add it to an end-to-end toolkit. To be fair, there are plenty out there which do that already. But still, if you guys want to do something of your own, you can check my GitHub, take the code from there, and trust me, it's really bad. I'm not a programmer, so help me out. Let's make that toolkit together.